Hello, welcome to this video. Today we're going to talk about this problem which was recently posed by blackpenredpen. So it is as follows. So take two integrals. So the first one will be the integral from -1 to 1 of square root 1 minus u squared du. So let's evaluate this integral real quick. So we know an integral indicates the area under the graph of a function. So we're going to draw this function's graph. So say this is u, this is square root 1 minus u squared, and actually what you get is a semicircle with radius 1. And the integral from -1 to 1 indicates that we're taking the area from the point x equals -1, which is this leftmost point, to x equals +1, which is our rightmost point. And you see the area we get is just the area of a semicircle with radius 1. So the area is going to be pi times 1 squared over 2, since this is the area of the entire circle. But because we're taking half of the circle, we have to divide by 2, and that results in pi over 2. So this integral evaluates to pi over 2, nice and neat. And take another integral from -1 to 1, but this time of 1 over 1 plus t squared dt. Now this function's graph is not nice or like a circle or something, so what we're going to do is just have to directly evaluate this. The integral of 1 over 1 plus t squared is arctangent of t, so this is going to be the arctangent of t, and this is going to go, t goes from -1 to 1. Now, arctangent of 1 is pi over 4. Arctangent of -1 is negative pi over 4. So in total we get pi over 4 minus pi over 4. It's pi over 4 plus pi over 4, which is also pi over 2. So now, the question proposed by blackpenredpen is there some substitution that we can use to go from one of these integrals to the other? Say, from this integral to this integral. Is there some t equals fu that we can use here that will get us here? So that's what we're going to explore today. So let's take the substitution that goes from here to here. And look, and let's write our substitution as t equals f of u. So first of all, because we're going to have to plug u in here to get this function, I'm also going to assume f is inversible, which later I'm going to actually show so after we get f to be a specific function, I'm going to actually show it is invertible. But for now, let's assume f is invertible. So we can say u is f inverse of t, which we're going to write as gt. So now let's use this. No. Okay, so when we substitute t equals f of u, first of all, for f to be a valid substitution, we want f to be 1 to 1, but again, because we are plugging in u equals the f inverse of t, what we actually want is f to be inversible. That is, there is some function which, after doing f and then this function, will yield the exact same result. So f of f inverse of x will yield x, and f inverse of f will also yield x. So these are the two requirements for f inverse to be the inverse function of f. If f inverse is inversible, f inverse, this is defined, this is the symbol for the inverse function of f. And that's what we're requiring here. So we want f to be inversible. Next, let's look at the bounds. So after applying f to both of these bounds, we want it to stay the same. We want f of -1 to stay -1, and f of +1 to stay +1. So we want f of ±1, which represents the bounds, to stay ±1, which represents the bounds on this side. Now, let's get to the actual substitution part. If we are plugging in t equals fu, or u equals gt, where g is the inverse function of f, we're gonna get this. So we'll have square root 1 minus gt squared, and then remember, if u is gt, du, I'm gonna write this. If u is gt, du is dg over dt times dt. So g of t is u, so this is just really the chain rule, sort of. So what we're going to get is this is the derivative of g. So this is going to be g prime, and multiplied by dt, we want this to be 1 over 1 plus t squared times dt, or in other words, if we just ignore the dt part, we want this to be satisfied. And as you might notice, this is a differential equation. So let's solve it. So what I'm going to do is integrate both sides here. This integral will be with respect to t. This integral, because we're multiplying by g prime, it will be with respect to g. So we'll have the integral of 1 over 1 plus t squared dt equals the integral of the square root 1 minus gt squared dg. So I'm not going to write gt squared here, because now in this integral, g is in itself the parameter. So g of t will be sort of saying that this is a function and we need to use t as a parameter, but no. Here we have an integral of g. Alright? So let's see. Here we have the arctangent of t, which is this. We want this to equal this integral. Now, we just need to evaluate this. I'm going to use a substitution. So let me write g equals sine theta. And by the way, this substitution is valid because this integral, because sine theta does not seem like a function that's inversible or 1-to-1, where 1-to-1 is a requirement for a function to be, is a requirement that a function needs to have for it to be valid in use of a substitution. But here, because this function is only defined between -1 and 1, like the biggest interval that this function can be defined on is from -1 to 1, and in that interval, the arcsine of g, which is what theta is indeed 1-to-1. It's even inversible, I believe. So there is no problem with that substitution. Just wanted to clear that up so there's no confusion. So if g is sine theta, dg is cosine theta d theta. So we're going to have the integral of what? Well, sine theta squared is, so sine squared theta, and 1 minus it is cosine squared theta. square root of cosine squared theta is cosine theta. And then we're multiplying by cosine theta d theta, which is our dg. So in total we have the integral of cosine squared theta d theta. Now, here I'm gonna use a double angle identity, which is that cosine squared theta is 1 plus cosine 2 theta over 2 d theta. Now, I can evaluate each part here separately. The integral of a half is 1/2 theta. The integral of cosine 2 theta is sine 2 theta over 2. And then divided by 2 again will be sine 2 theta over 4. So now, theta is arcsine of G. And sine 2 theta, I'm going to use another double angle formula, which is that sine 2 theta is equal to 2 sine theta cosine theta. And if I plug this in here, I get just sine theta cosine theta over 2, because this 2 cancels out. Sine theta is g, cosine theta is square root 1 minus g squared. So if I bring this a half outside, we get just arcsine g here plus g square root 1 minus g squared. And then plus c, of course. So we solved our differential equation. So we got something with t equals something with g. Now we started with, so g is the inverse function of f, and we want maybe to get back in terms of f, and the way we're going to do that is g here now represents a function of t. Here we just calculated its integral as if it was its own parameter, which in a sense it is. But now we are treating it again as a function of t. So g is a function of t. It means that because g is the inverse function of f, if I plug in here t equals f of t, g of f of t will be t. Because we define g to be the inverse function of f. So after substituting that in, we'll get that the arctangent of f of t is equal to 1/2 of arcsine t plus t square root 1 minus t squared plus c. Okay? And then if we apply tangent on both sides, we'll get f of t. But before doing that, I want to satisfy these other two conditions. So I satisfied this condition. Now let's move on to this condition. So we want f of plus minus 1 to be plus minus 1. So if we plug in here t equals plus minus 1, what are we going to get? So t equals plus minus 1. The f of plus minus 1, we want it to be plus minus 1. The arctangent of plus minus 1 is plus minus pi over 4. We want this to equal half the arcsine of plus minus 1 over 2, which is plus minus 1, which is plus minus pi over 2. Now, t here is plus minus 1, so this is going to be plus minus 1 times the square root of 1 minus plus minus 1 squared. Now, both positive 1 and negative 1 give 1 after squaring them. 1 minus 1 is 0, so this entire thing will be 0. Meaning that we can close the brackets here and add c. Now this is plus minus pi over 4. So what we're essentially saying is we want two equations to be satisfied. Pi over 4 equals pi over 4 plus c. and negative pi over 4 equals negative pi over 4 plus c. As you can see, both of these are satisfied if and only if c equals 0. So, if we use c equals 0, so we basically just ignore this addition of plus c, we ended up with not an infinite family of functions, but one function f of t, which now satisfies this requirement. Now, this is getting a little crowded, so we're going to clear the board, and after clearing the board, we're going to show that this function f really is inversible. Okay? So, just as a quick recap, we want to show that this function is inversible. F of plus minus 1 is plus minus 1, and that it satisfies this differential equation. So we already showed these two. In fact, we got f from this differential equation. Now we just need to show f is inversible. So what I'm going to do, first of all, I think you'd agree with me, on t from negative 1 to 1, I think you'd agree with, on the interval from negative 1 to 1, I think you'd agree that this function is continuous. So there are no functions that break there, break anywhere. In fact, if you plot it, you get something like this. Alright, it's a bit exaggerated, but that's essentially sort of how it looks. So it's continuous, and there's no reason why it shouldn't be continuous, because on the interval from negative 1 to 1, this is continuous, their sum is continuous, one half of them is continuous, and their tangent is also obviously continuous. So this function is continuous. Now we're just going to show that this function is monotonic. So if you plot its graph, you can sort of see it always goes up. We're going to actually prove it. So first of all, I'm going to write this as tangent of h of t. So I said this part is ht. I defined h to be the part inside the tangent. Now I'm going to take the derivative of f. So df dt. Well, let's use this form. So first of all, by the chain rule, it's going to be h prime t times the derivative of tangent of h with respect to h, which is just secant squared ht. Now, remember what ht is. Ht is this thing. But remember how we got this thing? We got this exactly from integrating square root 1 minus g squared. And what we got is the same thing, but yours was placed with g. So if we take this derivative with respect to t, we'll have to exactly get the square root of 1 minus t squared. Meaning that this is the square root of 1 minus t squared times secant squared ht. Now, if we look on the interval, the open interval from negative 1 to 1, this will always be positive, strictly positive. So, because this 1 minus t squared will be strictly positive, so its square root will be strictly positive, and secant squared, you might say, well, that could be bigger than or equal to 0, maybe it's at some point is 0, but remember, secant of something is defined to be 1 over cosine something. So if the secant is 0, the cosine would have to be infinity or negative infinity, which is obviously impossible. So this is strictly bigger than 0. Meaning that f is strictly monotonic. So it basically means if I have t1 that is strictly less than t2, that implies f of t1 is strictly smaller than f of t2. So it always goes up and there are no like breaks in between. So how can we use this to prove that f is inversible? Well, first, so we want to show f is inversible, and f, remember, is going from the domain of the closed interval, negative 1 to 1, to the same interval, the closed interval from negative 1 to 1. So, if we show that each number here corresponds to exactly one number here, then by definition we've proved f is inversible. So first of all, let's show that for any value x here, there exists some y. For every value y here, there exists an x here, which f of x is equal to that y. So let's see. So first of all, for y that is plus minus 1, obviously there is such an x. That x would be plus minus 1, as we've shown. And maybe to reassure yourself, you can also just plug in a plus minus 1 into here and get that this entire thing turns to plus minus 1. If you don't believe me on this, you can check that on your own. But now, for y not plus minus 1, it means that y is on the open interval from negative 1 to 1. And if y is on the open interval from negative 1 to 1, that means negative 1 is smaller than 1 is smaller than 1. And because f is monotonic and continuous, well, we actually only need that f is continuous. But because f is continuous, that means that for every value between negative 1 and 1, there has to exist an x such that f of x is y. And the intuition behind this is, look, if this is continuous, this is like a line you can draw without removing your pen. So say we're at some level y, then if you have to go from y level negative 1 to y level 1, and y is strictly between negative 1 and 1, you're going to have to go, you might be doing all sorts of weird things. Maybe it's, even if it's not monotonic, maybe you have like little humps here, something here, but eventually, because you're going to have to end up at 1, you're eventually going to cross it at some point. So, which is the same as saying there exists an x, so that f of x is equal to y. I've proved this statement in a previous video, which and that video was about doing my Calc 1 exam. I did my Calc 1 exam, posted it to a video, and the first question was basically proving this statement. So I'll leave a link to it, and you can go watch it if you want to see the formal proof of this statement. But if you're just fine with the intuition, or you already know what the proof is, this is essentially it. So there exists an x such that f of x is equal to y, meaning that indeed, we've shown one thing that we wanted to. Now we want to show that this x is unique. So what we're going to do is, let's do it here. Assume there are x1 and x2, such that f of x1 is equal to f of x2, which is, say, equal to the same y. So if we assume that x1 and x2 are different, we can also assume x1 is smaller than x2. without loss of generality. And this will leave us, because f is strictly monotonic, that f of x1, which is equal to y, is smaller than f of x2, which is equal to y. So in other words, y is smaller than y, which is impossible, meaning that if x1 is not smaller than x2, and obviously by the same reasoning x2 is not smaller than x1, x1 has to be equal to x2, which is pretty much the definition of unique. If there are two numbers which a number is unique in a number that satisfies some property is unique if you can show that two numbers satisfying these two properties have to be the same number. So that's practically the definition of unique, or at least a way to prove it. So we've shown that each y corresponds to an x, and we've shown that each one of these x's is unique. So in other words, a unique x corresponds to a unique y, which is the definition of inversible. So we've shown this, and we've shown all our requirements that we've used or are just mathematically needed. So finally, if we use this substitution, so what we did here is essentially a function for t, but this function really needs to be of u. So if we substitute t equals f of u, into the integral of square root 1 minus c squared. You can check for yourself. It does indeed turn out as 1 over 1 plus t squared. The bounds stay the same. Everything is good. The substitution is valid. And we'll end up with we ended up with exactly what we want, a substitution from one of these integrals to the other, a direct substitution. And finally, that's it. If you want more content like this, please subscribe to my channel. I'm uploading more interesting problems and things like this in the future. And finally, that's it.